So my talk today is called Robust Generalized Bayesian Inference for Intractable Likelihood. And it's a talk in collaboration with three people. Takeo Matsubara is a PhD student at Newcastle University and the Alan Turing Institutes. Jeremiah's and FX are well known to everyone in the call. And I'd just like to highlight that the work I'm going to talk about is really led by these three co-authors, and I'm the junior author in this work. I'm very happy to be the junior author. So the title has already given away that this is about intractable likelihood, and the word intractable actually has many different uses, so I need to be more specific. The kind of intractability that we're going to talk about today is what you might call an intractable normalizing constant. So we're interested in parametric statistical models, and we're going to assume that they have densities for simplicity. The density is going to be written p subscript theta of x, where theta indicates the parameters of the model, and x is a dummy variable representing values that theta can take. And we call a statistical model like this an intractable statistical model or intractable likelihood if it's written in the form of a numerator, which is an easy to evaluate explicit function, and a denominator which is difficult to evaluate or requires computational resources beyond what we're prepared to invest to evaluate. Now, many statistical models fall into this category, and in fact, generic exponential family models are intractable likelihoods. So here's the canonical exponential family with natural parameter theta, sufficient statistics t, and this is generically intractable. The normalization constant will not have a closed form. Now, of course, often you'll be able to approximate this computationally without too much hassle, but you know, generally speaking, this is not explicitly normalizable, and it contains a wide variety of models that are actually very widely used. So here's an example of well, the equation here on the left is the classical Ising model, but the picture is a Potts model, which is the multi-category generalization of an Ising model. These models are used to study data that are naturally arranged on a grid. And another kind of intractable, well, sorry, let me just expand on why this is intractable. So if we wanted to normalize this statistical model, we would need to consider summing over all possible configurations of states on this grid. And as you know, this is a combinatorially huge number of states, meaning that evaluation of the normalizing constant will be intractable in general. And another example, which is perhaps more important, is energy-based models. So this is a statistical model widely used in generative modeling in machine learning. And the idea is that you have an exponential transform of some complicated parametric function. And the role of the exponential transform is to make sure that probabilities are non-negative. And the complicated parametric function may be something like a neural network. The idea is that by learning parameters in an appropriate way, you can learn to generate complicated structured data like image data. And this is, of course, intractable again, because to normalize a statistical model like this, we need to explore all possible configurations of x. And if x is an image, for example, even if the different colors are taking finite values, it's still a huge space to explore. So these are important examples of intractable likelihood. And the problem of intractability gets even worse when we try and do Bayesian inference in this setting. And that's due to the familiar fact that in Bayesian inference, the marginal likelihood is also typically an intractable normalization constant. So if I write down here the posterior, we've got the marginal likelihood and the intractable normalization constant from the intractable likelihood. And this situation is often called a doubly intractable posterior. So that's unfortunate because these statistical models are as deserving as a Bayesian treatment as other statistical models, but the Bayesian framework is severely computationally limited in this intractable setting. So there are some attempts to resolve this problem that take a computational stance. There are auxiliary variable Markov chain Monte Carlo methods, for example, and some other classes of methods which are applicable when you can simulate from the statistical model for fixed values of the parameters. And that's not necessarily the case with those examples I just showed. I also want to highlight that the computational challenge here is so difficult that the other kind of statistical considerations that we might naturally think about, like robustness to model misspecification, they're given relatively less attention because, well, first we've got to deal with this computationally very difficult problem just to perform standard Bayesian inference. So there's very little work on robust inference in this context. And this talk is about robust Bayesian-like inference for intractable likelihood, where there's very little work at the moment. Now, we're going to propose a particular approach to parameter inference in this context that fits within the general framework of generalized Bayesian inference. And I'll explain what that is shortly. But just to preempt where we're going to advocate for posteriors or generalized posteriors or pseudo posteriors, whichever name you prefer, of the form on the screen here. So let's just say we're going to advocate a particular kind of generalized posterior that involves something called a Stein discrepancy, and the reasons for that will become clear later. But what we're going to end up with is a framework for inference that is both computable, it's going to circumvent all these computational issues involving intractability, and it's going to be robust in a very precise sense that we'll make clear shortly. So that's where we're headed, and the contributions are essentially what I just said with some additional theory.
Sorry, Chris,
yes.
What's the preamble?
Okay, so Sam has pointed out quite rightly that I'm using notation on this slide that I've not defined. We'll see in a second, but p theta is going to be the distribution whose density was p theta, and Pn is going to be the empirical distribution of the data, but this will all become clear later. Yeah, apologies for that. Okay, so in order to do this, I'm going to need to cover some background, and I'm going to start by covering generalized Bayesian inference, and then I'm going to cover Stein discrepancy, and then we'll put it together to explain what that generalized posterior on the previous slide was supposed to mean. So generalized Bayesian inference takes a particular view of Bayesian inference as the solution of an optimization problem. And to set that up, let's just observe that we can re-express the standard Bayesian posterior in the following form. And I've just exploited exponentials and logarithms to write a normalized posterior density in this way. And what generalized Bayesian inference does, just operationally, is it replaces the sum of the log likelihoods evaluated at data. Just to point out, so here we're implicitly assuming independent IID data xi. It replaces that sum of log likelihoods with some sort of data-dependent loss function, which can be quite general. So why does it do this? Well, first of all, let's just point out what a data-dependent loss function may be. It could be a divergence type loss or a score matching type divergence. It does this to confer robustness. And why would that confer robustness? Well, so typically, Bayesian inference performs very badly under model misspecification. And the reason for that is the likelihood is entirely rooted within one particular statistical model. And the likelihood is basically determining where your posterior probability concentrates. So if you're not able to sort of acknowledge the possibility that the model may be wrong or that data may be coming from some sort of perturbed version of the statistical model, then you're going to run into problems. And asymptotically, you may be arbitrarily confident about a particular configuration of parameters that is incompatible with the data generating process. So by replacing the log likelihood with some other loss function, we may hope to be able to avoid this problem of Bayesian inference becoming overconfident in misspecified regimes. Okay, so I've indicated some loss functions here. These are all motivated in some way, either because of their robustness conferring properties or because of computational properties, and we're actually going to see both in this talk. But why this formulation? Why exponential of negative loss? Well, that comes from this view of generalized Bayesian inference being an optimization procedure. We can actually show, and Jeremias is the expert in showing this, that the standard Bayesian posterior solves the variational problem, which is to minimize over all possible probability distributions rho this expected loss and KL regularizer. And what we're doing in generalized Bayesian inference is replacing the negative log likelihood loss with a general data-dependent loss function. And if you do that, the solution of this variational problem is precisely this form of generalized posterior on the first line. So that motivates this particular form, but we of course need to argue for a sensible choice of data-dependent loss function. Now, in this talk, we are motivated first by computational considerations, the intractability of the normalization constant, and then by robustness. But first, to deal with that intractability of the normalization constant, we're going to propose using a Stein discrepancy as our data-dependent loss function. So to do that, I need to briefly introduce what a Stein discrepancy is. And it's a sort of technical object, but it's got a huge number of uses in both theoretical and computational statistics, as well as applied probability where it originated. And the key concept here is the Stein operator. So the Stein operator takes as input something, which in this case will be a function from a set of functions calligraphic h, and returns another integrable function with the property that the expectation of the Stein operator applied to a function of x is 0 for all functions h in that Stein set. So that's just a mathematical definition, but it's focusing on something concrete. So this operator here is called the Langevin Stein operator. Q is going to be the density of a probability distribution Q. We look at the gradient of the log density, and we take an inner product of that with a vector valued function h. We add to that the divergence of this vector field h, and we get a scalar valued function of x, which we can integrate and will give us 0 if we integrate over q, subject to some boundary conditions. Okay, so those are examples of Stein operators. So what's the Stein discrepancy? Well, it says, suppose that we have another distribution p, which may or may not equal q. Well, we can measure how similar p and q are by looking at the extent to which this equality is violated. So we know that if p equals q, by construction, all of these expectations should be 0. So if p is not q, well, then let's look at the expectations that are not 0 and use those to measure, in some sense, how different p is to q. And one way to do that is to take a supremum over all of the functions h that could have been operated on by this Stein operator, taking a supremum over the values of the expectations that we get. And that's called a Stein discrepancy. It has a couple of really important properties in this context. The first property is that Stein discrepancy can be computed without the normalization constant of q. And you can see that if you look at the Langevin Stein operator, for example, because it involves the gradient of the logarithm of q, and that can be computed with an unnormalized representation of the density q. So that's going to be useful, and you can see that's going to deal with this problem of intractable normalizing constant shortly. The other important property is that it only requires expectations with respect to p, but not q. So if q is a distribution that's quite difficult to do manipulations with, like, for example, an intractable statistical model, then that's great, because we don't need to take expectations with respect to q in order to evaluate the Stein discrepancy. And you can contrast that with, for example, an integral probability metric, which would involve expectations with respect to both p and q. That's Stein discrepancy. The actual calculation of Stein discrepancy, in principle, looks quite challenging, because not only does it involve expectations, integrals, it also involves supremums. But it turns out there's tricks that we can use to make this quite straightforward. So let's take a look at that. So we need to specify the set of functions h that we're taking the supremum over, and then we need to come up with some tricks to deal with this, with this term here. So we're going to take for that set h the unit ball of a reproducing kernel-Hilbert space. So I'm not going to attempt to define a reproducing kernel-Hilbert space here, but the key property of such a space is this one here, with a reproducing property. And that says that we can write an element of this unit ball, which is a function h. We can write it as the inner product of, well, the function h. We can write evaluations of h at a location x at the inner product of h with the bivariate function k called a kernel, and the inner product is taken with respect to the inner product on this reproducing kernel Hilbert space. So the details, in a sense, don't matter, but what matters is, well, we've got this reproducing property that we can start to substitute in to this expectation. And let me just sort of loosely indicate that if you're trying to take a supremum over something which takes the form of an inner product, well, then we have a result called Cauchy-Schwarz, which tells you that there's an upper bound which is attained. Now that's going to allow us to explicitly evaluate this supremum in closed form. So imagine taking H, plugging H in here, using this inner product representation, exploiting the bilinearity of the inner product to bring these expectations inside. Then the supremum of the absolute value of an inner product, Cauchy-Schwarz says it's attained, and it tells you what the maximum is. So we have a closed form expression for Stein discrepancy, and in this case, we call it a kernel Stein discrepancy. KSD is the acronym that's usually used, and the square of this kernel Stein discrepancy has this convenient form here. It's the expectation with respect to two independent copies of a random variable whose distribution is P of this object here. This is obtained by taking your reproducing kernel and applying a Stein operator once to each argument. And the Stein operator is designed with the distribution Q in mind. So think of Q being the model that you'd like to approximate. Q is fixed, and we're interested in varying P. And there's a technical point here, which is that the kernels I'm talking about are going to be matrix value kernels, but that's not very consequential for the rest of the talk. Okay, so well, that computationally resolves a problem that we had with Stein discrepancy, but is it a sensible choice? And how reasonable is this Stein discrepancy? Does it meaningfully quantify some sort of difference between P and Q? And the answer is it depends on the kernel, minimally. So some quite technically challenging applied probability and analysis has been able to establish that this is sensible in some situations. So it turns out kernel Stein discrepancy and the convergence of that to zero actually implies the weak convergence of a sequence of distributions Pn to Q. So that's nice. That's what you might call convergence control. And there's various forms of these results and various forms of the converse result as well. So we have some theory that supports the use of kernel Stein discrepancy as a means to measure the departure from Q of another distribution P. So our proposal, which I'm going to call Stein discrepancy Bayes, is to use a Stein discrepancy as the data-dependent loss in a generalized Bayesian posterior. So concretely, our generalized posterior has a density, assuming that everything has densities from this talk, which is the product of the prior density and the exponential of negative Stein discrepancy squared times n. And I'll explain why. Well, actually, I won't because of time, but I can explain why this is the right way to include Stein discrepancy. This too is not arbitrary. Okay, so what does this mean? Well, if we use kernel Stein discrepancy, then we have an explicit form for the generalized posterior, which we can compute for an intractable statistical model, provided that we can differentiate the log likelihood, which is something that we can often do in these cases. And if we have IID data, x1 to xn, then what we're doing is we're evaluating this object at all pairs of that data. Okay, so that deals with computation to an extent, and I'll explain more later about why this object is particularly convenient for computation. But you can already you can already see that this is something explicit, right? So there's no intractable normalizing constants here, but it's even better than that, and I'll explain why later. But the other question that we had was about robustness, and this generalized framework is quite nice because it allows you the ability to change the way that you do inference in order to account for the kinds of model misspecification that you're able to anticipate, essentially. So if you are analyzing a data set which may or may not contain outliers, you can at least sort of have an idea what an outlier might look like, what kind of extreme values are unlikely to be real. And you can use the degree of freedom that's provided by generalized Bayesian inference in order to mitigate that to some extent. So precisely, we've got a kernel here, and we can choose that in order to confer robustness of some kind to this generalized Bayesian framework. And that's what we're going to talk about later as well. Yes.
Probably stupid, but so what you're doing here is not the same as replacing the KL in the representation that you showed earlier with the Stein discrepancy. Is it?
No, that's right. So, as Jeremiah's paper makes a very sort of clear argument for, where there are three things that you can do to come up with a generalized Bayesian procedure. You can either change the class of distributions that you're optimizing over, the loss function, or the regularizer. And here we're changing the loss function. Thanks, Sam. So I said that the computational story is even better than just having an explicit form of the generalized posterior. It actually permits fully conjugate inference for canonical exponential families. So let's take a canonical exponential family. It's going to turn out that the Gaussian prior, or at least a prior with a Gaussian density that may be truncated if the parameter space is bounded or something, is conjugate in this case. So the posterior is again Gaussian, and it has an explicit mean and covariance that can be computed. And that's extremely surprising, because if you think about the computational effort that would be required to perform Bayesian inference for an intractable likelihood, you would be running something like an auxiliary I can't even say it, let alone do it, auxiliary MCMC algorithm, which is, not only inherits all the complexities of tuning and implementing MCMC, but it requires additional bells and whistles. So to contrast that with closed form expressions is quite surprising, I think. And there is a computational cost still, and it's quadratic in n, the number of data, due to some of the matrices that appear in these formulae. But it's a quadratic cost for an exact posterior, as opposed to a linear cost per iteration of a particularly challenging type of Monte Carlo algorithm. So I think this may still be quite attractive in many situations.
Sorry, Chris, Ivanis Cosmidis here. Isn't this cubic because you have to invert the matrix?
Question from Johannes, thank you, yes, about whether this is a cubic.
It's between quadratic and cubic, I think, but it's not exactly quadratic, right? Because you have to invert the matrix.
So you're observing that this matrix inverse is here. So these are actually matrices that are of the same dimension as the parameter, and not as the number.
Oh, right. Okay. Sorry about that. Yes. Okay, that makes sense. Right.
Okay. Oh, sorry. So I'm just broadcasting the question for the room. So Johannes was asking, is the cost not cubic because there are matrix inverses? And yeah, I was highlighting that the matrices here are as the same dimension as the parameter. The quadratic cost comes from assembling some of these quantities. So you can see that there's a double sum over something of size n. Yes, that's the quadratic cost.
All right, thanks.
Thank you. Okay, so just a brief nod to theory. I'm not going to go into too much detail. We can talk about consistency as a sort of minimal kind of theoretical result. So we'd like to say that if we obtain more and more data, we would like our generalized posterior to concentrate around the value of the parameter, which minimizes the Stein discrepancy. And you can formulate concentration in various different ways, but the way that we do it is written here. So for all positive values of delta, we'd like to look at the difference between the discrepancy, and just to point out, D here is the squared KSD. It's just simplified notation. The discrepancy between the best fitting model according to our discrepancy and the data generating distribution. And we compare that with the same quantity integrated over values of theta generated from the posterior. So we can show that the probability associated with this difference being greater than delta tends to zeros and tends to infinity. And there's various pictures here which show you what's going on a bit more intuitively. So this is our generalized posterior. This is the discrepancy between the data generating model P and our parametric model P theta. There's a best value of the parameter according to this discrepancy. And our generalized posterior is going to concentrate on that best value as n goes to infinity. Okay, so what conditions do we need for this? Well, the way that we've formulated this is quite closely based on some previous work by Pierre Alquier and colleagues. And it involves something called a prior mass condition. So we assume that the prior is continuous and positive at this best parameter, which is quite a weak assumption. And then we assume something which those authors called a prior mass condition, which is more technical, but still not too strong. What it's saying is that there's enough prior probability in a small region around the true, around the best parameter value. So it's essentially a strengthening of this first condition. And under those two conditions, we have an explicit upper bound that gives us posterior consistency as a consequence. Okay, and all the details behind this theory are in a preprint, which I'll give you the link to at the end of the talk. So consistency is great, but it's sort of just a first step, and we'd like to know a bit more. So it's very common to ask about fluctuations and whether these posteriors are asymptotically normal, and that is also the case here. So we show asymptotic normality in the paper. I don't know how illuminating it is to discuss this, really. I mean, we are hopefully familiar with the idea that if you rescale by centering at the value of the parameter which minimizes the discrepancy between the parametric model and the empirical distribution of your data, then the fluctuations will be asymptotically Gaussian. So here, Pn, just to clarify, this is the empirical distribution that gives equal weight to all of the data points in the data set. Okay, so asymptotic normality. Our assumptions are deriving from a general framework for proving Bernstein von Mises results that was proposed by Jeff Miller in this, we've called it 2019 paper, but I think it's published as 2021 now. And they're smoothness conditions. So we require assumptions on the smoothness of the derivatives with respect to theta of the Stein operator, and also a moment condition and continuity of the mapping from H to derivatives of the Stein operator. So they're sort of high-level mathematical conditions that can be directly verified for models that you're prepared to write down, but I state them abstractly here. So here's the precise result. So we've got this total variation type convergence, almost sure convergence to a Gaussian. And the asymptotic precision matrix here is based on the Hessian of the squared KSD evaluated at the most appropriate value of the parameter. So provided that this asymptotic precision matrix is non-singular, then we have this asymptotic normality result. And we'll actually use this later to talk about the calibration of these generalized posteriors. So I haven't provided any reason for you to think that this asymptotic covariance matrix is suitable. You know, it may be overconfident, it may be underconfident. This is not clear yet. Let's talk about robustness first, because that's our main motivation here. We want to deal with the kind of problems that we would almost, have been expected to deal with if we were performing a standard Bayesian analysis. We would want to check that our model is reasonably specified. We might look at prior predictive distributions, for example, or there's all manner of checks that could be done, and we're typically not doing those checks in the intractable likelihood setting because we're just so focused on this computational challenge. But let's try and deal with these kind of robustness questions in the context of intractable likelihood. Now, what does it even mean to talk about robustness in a Bayesian setting? There's lots of different interpretations, right? So we could talk about sensitivity to price specification, all sorts, but we're going to consider one particular type of robustness, which is at least sort of easy to analyze, as well as being practically relevant. It's called contamination, and we're going to consider what's called an epsilon contamination model. So Pn are going to be the empirical distribution of the, Pn is going to be the empirical distribution of our data set, and we're going to consider removing a small amount of that data set, so basically multiplying it by 1 minus epsilon, and adding in a Dirac mass centered at some location y, which is out of sample, so which is not typical of our data set. And we're going to ask how much the addition of that y, which we call the contaminant, changes the inferences that we make about the parameters. So here's just a picture. So this is well, the histogram, I guess, is Pn here, and we're going to add in a data point which is unrelated, or at least very far from the data set. So how can we quantify the change in the posterior? Well, it's clear how to do this from a parameter estimation point of view. So if we have an estimator of theta that's a function of our data set, then there's a classical literature which talks about influence functions. The influence function is defined as this, essentially the sensitivity of the parameter estimate to small perturbations in the direction of y. So the derivative of theta hat with respect to epsilon value to the epsilon equals 0. That's a classical quantity. If that influence function is actually bounded over all possible values of y, then we say that that estimator is bias robust. So here's a picture. So the blue line here represents an estimator, I guess for a mean in this case maybe. And if we add a contaminant to the data set, it's changed the value of our estimator by a amount, delta. So the influence function measures how much this estimate has changed when we've added a small amount of contaminant. But if this estimator isn't going to move arbitrarily far, even if we take this contaminant all the way off the edge of the screen, then we say that the estimator is bias robust. So let's introduce a Bayesian analog of this. We're going to follow Ghosh and Basu and introduce the posterior influence function. And the idea is almost the same as in the point estimation context, except instead of point estimate, we're going to look at point-wise evaluations of the posterior density. So we've replaced an estimator with the value of the posterior density evaluated at a particular location theta. And everything goes through as before, except when we talk about bias robustness, we're going to also take a supremum over values of theta, because you can think about this as being an infinite collection of point estimators indexed by theta. So we'll take an additional supremum over theta. And if this double supremum of the posterior influence function is finite, then we will call our generalized posterior globally biased robust, where globally basically refers to this additional supremum over theta. So again, the picture is the same. If we add some contaminant and we push that contaminant very far away off the screen, we would call the generalized posterior globally biased robust if this posterior basically doesn't disappear off the screen too. So under some quite general conditions, we can establish sufficient conditions for global biased robustness of generalized Bayesian procedures with quite general data-based loss functions D. And the two conditions that we require are stated here, but I'm just showing this result as a sort of just to flag that there's a more general framework that we've got here. And what we're going to do is we're going to plug in kernel Stein discrepancy squared as D, which yields an explicit sufficient condition for global bias robustness of this Stein discrepancy based procedure. So what we require is a particular property of this kernel function. So remember, that was the aim. We had this kernel as a degree of freedom, which we could choose in order to confer different kinds of robustness properties on our generalized posterior. So we're going to focus on global bias robustness, and we're going to pick this kernel K in order to give us global bias robustness. And what do we need K to satisfy? We need this supremum to exist, to be bounded by some function gamma, and that function gamma needs to itself satisfy some sort of bound and integral moment type condition. And we can do that explicitly for all of the models that we looked at in this work. So what that gives us is, and this may be a bit of a bold claim, but I think that's okay. So we have a principled approach to robust generalized Bayesian inference that is applicable to intractable likelihood. And we claim to be the first to do that. So let's have a look at some experiments in the last 10 minutes or so. This is a sort of recap slide, and it explains how you would go about implementing this generalized Bayesian approach. I hope I didn't give the impression with some of the previous slides on theory that this is complicated to do. It's actually very easy to do. So we have an explicit formula for the KST Bayes posterior, and that even reduces to an explicit Gaussian posterior with mean and covariance matrix that I can give you formulae for in exponential family models, in canonical exponential family models. And all we need to do is pick the kernel K. So what's required? Well, there are 3 terms in this kernel that are relevant in different respects. The first is just a scalar, which determines the overall scale of the kernel. And that's going to be something that's critical in calibrating the generalized posteriors that we get. Because through increasing or decreasing beta, I'm going to directly multiply this loss function by beta. And that's going to entirely determine the scale of these generalized posteriors. So selecting beta is going to be absolutely critical. The second term is essentially, the thing you would normally recognize as a kernel, some way of measuring the difference between 2 inputs, or the similarity between 2 inputs. And we've adopted here a particular kind of kernel called an inverse multi-quadrant kernel. Now, the reason we've done that is partly heuristic, in the sense that this kernel is known to work well in similar sort of applications, but also because the kernel Stein discrepancy with this kernel has been shown to enjoy weak convergence control under reasonable assumptions, and that seems like a good rationale for picking a kernel. But just to add an aside, we don't need weak convergence control here. We just need to distinguish between different elements in the parametric family. But by having weak convergence control, one would hope that we could also distinguish between a strict subset of those distributions too. And the final term here is, we don't really have a good name for this. We're calling it the weighting function. But this is the degree of freedom that we're going to use to confer global bias robustness. So here, M is a matrix, and you may remember I said there's this technical issue that we have a matrix-valued kernel. It doesn't matter particularly. The point of M is that it's going to either upweight or downweight the importance of different kinds of data, depending on what kind of robustness we're looking for. So in experiments later, we'll see, well, maybe very large values of X are unreasonable, and M would essentially take smaller values or downweight the influence of very large values of X. That's the kind of role of M here. Right, let's just have a quick comment on setting of beta. Now, that turns out to be extremely challenging, and it's actually an open problem in generalized Bayesian inference, how to select beta in general. Beta should be chosen in order that the credible sets produced using this generalized Bayesian framework are calibrated in some sense. Now, there's a couple of papers that explore different ways to do this, and for the present purposes, we adopted one way, which is not perfect, but it's quite practical, which is due to Lydon et al. And what it does is it compares the posterior precision matrix that we get from our Bernstein von Mises result with the asymptotic precision matrix of the minimum Stein discrepancy estimator. Now, what that enables us to do is to take an estimator whose asymptotic error is something that we can characterize and that we know, and we can set the scale of our generalized posterior such that the credible sets are commensurate with the accuracy of that estimator. And there's no unique way for how one should do that. What we do is we measure the size of the precision matrix using the trace. So this is the trace of our posterior asymptotically, a trace of our posterior precision matrix asymptotically, and this is the trace of the asymptotic precision matrix for the minimum Stein discrepancy estimator, and we take the ratio of these as our weight. Okay. Now, what we do further is we approximate these matrices, because these are asymptotic precision matrices which are unknown, and we need to approximate them. We do that in a fairly obvious way, which I've not included in this slide, but we use essentially samples to approximate these information matrices. And that can confer some numerical problems, because at small sample sizes, approximating these matrices can be difficult. And in fact, there's a matrix inverse here too, which exposes your approximation error quite clearly. So we include a minimum of 1 with this empirical approximation to the weight beta here. And that just stabilizes our estimate of beta in the small sample size regime. Okay. So here's the first experiment. This is for illustrative purposes. It's a tractable model. So we don't need Stein discrepancy Bayes here, but it illustrates the idea quite nicely. The model is the normal location model. So the likelihood is a Gaussian likelihood with mean theta to be inferred and variance 1. Our data are assumed to mostly come from this Gaussian, but a small fraction epsilon of the data come from a different Gaussian that's centered somewhere else. Okay, now what I'm going to do is generate data from the model with true parameter 2, 100 data points, that's not so relevant. And we're going to explore how the generalized posterior changes when either the proportion of the contaminant epsilon or the location of the contaminant y are varied. So this first column here is what happens in the case of standard Bayesian inference, which is of course, conjugate in this case. So as we increase the proportion of contaminant, the posterior just shifts in the direction of the contaminant. And that's clear why that happens. So the contaminant is located at 10, which is sort of way off to the right here. And by taking the standard Bayesian posterior, that posterior probability mass just moves towards the contaminant. It's biasing the posterior. And the same is true if we increase the proportion of the contaminant, keeping the location of the same is true if we move the location of the contaminant, keeping the proportion of the contaminant fixed. KSD Bayes, whether or not that's robust, depends on our choice of matrix, weighting matrix M here. So if M is the identity, we may have global, no, apologies, no, we do actually have global bias robustness, but it's not sort of, it's not as a consequence of our theory. So our theory is not sort of necessary and sufficient. But if we pick a weighting function M here, which downweights extremely large values of X, then we can introduce robustness. So what we've done is we've picked a weighting function M to satisfy the conditions of our theory that guarantee global bias robustness is of the form something like 1 over 1 plus X squared. And the generalized posterior is now much less sensitive to contaminant. So you can see here, the proportion of the contaminant is fixed to 10%, and the location of the contaminant is moving from 1 to 10 to 20, and that posterior is hardly changing at all. So it's really insensitive to outliers in this case, and that's because we've introduced that robustness through our choice of kernel in the generalized posterior. Here's a second example. This is a two-dimensional precision estimation problem. I think we're trying to estimate two precision type parameters in an exponential family model. But otherwise, the considerations are the same as before. So we've got the Bayesian posterior here. So the truth is at the origin, and the posterior distribution is biased away from the true value of the parameter as either the amount or the location of the contaminant increases. So it's the proportion of the contamination is increasing from 0 in the top row to 10% to 20%. KSD Bayes, without putting any thought into how to choose the weighting matrix M, is not biased robust, not globally biased robust. But if we choose the weighting matrix M in the way that is presented to us in our theoretical analysis, then we confer global bias robustness on the posterior, and we sacrifice a small amount of statistical efficiency. So this posterior, you may be able to see, is slightly wider than the Bayesian posterior. And it gets wider still in contaminated regimes, but it's not moving quickly away from the true parameter values. It's discounting the outliers in this data set in a way that we deliberately encoded. This example, the previous example, and in fact all the examples you're going to see are conjugate inference. So everything I needed to compute was closed form for all these generalized posteriors. And the final example is intended just to show the kind of breadth of statistical models that are intractable likelihoods in the exponential family setting. So this is called an exponential random graph model. It's a model for high-dimensional data that tries to capture the negative correlations between different coordinates in a high-dimensional vector X. And it's been used in various different contexts. This particular example I don't think is scientifically very motivated because this is a biological example that involves protein interaction, and we know that protein interactions are not all negatively correlated, but this is kind of nice for illustrative purposes here because it's clearly a misspecified model. So let's see what happens when we compare KST Bayesian inference with no robustness built in to KST Bayesian inference with robustness built in. And just to caveat, I'm not able to show you what Bayesian inference does here because I don't have the first clue about how you would perform Bayesian inference in this case. I mean, I can't generate from this model. I can't do numerical cubature. I'm at a loss for how to do Bayesian inference here. So there's no comparison with Bayesian inference. KST Bayes is closed form in both settings, which I think is quite a stark contrast in terms of computational convenience. So what I'm doing is I'm presenting protein regulatory networks that were inferred using an exponential random graph model, and edge is present if and only if there's significant statistical evidence for a non-zero value of the parameter that controls the interaction between the relevant protein species. I'm cutting off edges after 5, so I'm showing you the 5 most strongly supported evidences in the dataset, edges for which there's evidence in the dataset, and I'm contaminating this model in a way which is described here actually. I'm throwing in a value of I'm throwing in a data point which has all of its entries equal to 10, which is essentially an outlier compared to this data set. And in robust KST Bayes on the bottom row, I'm introducing a weighting matrix M, which attempts to discount the influence of outliers of this kind. And what you see is as I increase the proportion from 0 to 1%, 2%, 5% of contamination in the data, the KST Bayes posterior changes massively to the extent that the inferred protein signaling networks I get are essentially totally different depending on the level of contamination. That's not robust in the slightest. The story is a bit better for robust KST Bayes. All 3 of these networks are the same, even though the proportion of contamination was increased from 1% to 5%. On the other hand, there is still a change in the network inferred when there was no contamination at all to when there was some contamination. So this perhaps also reflects the difficulty of these network inference problems, and it's sort of widely appreciated, although perhaps not in the systems biology community, but it's sort of clear that these high-dimensional structure learning problems are just really challenging generally. Okay, so that was the proposal. We've got generalized Bayesian inference with a Stein discrepancy as the data-driven loss function. And we believe that this is great for 2 reasons. One is that it gives you computable generalized posteriors. Now, they're either completely conjugate or they're intractable in the standard sense, that you can use standard MCMC algorithms and not auxiliary variable MCMC algorithms to sample from these. And we showed you how robustness, specifically global bias robustness of the generalized Bayesian posterior can be conferred by carefully choosing the weighting matrix M that goes into selection of the kernel. So that's great, but there's lots of open questions. Probably the biggest one is the behavior of this framework in situations where Stein discrepancy is known to have pathologies. It's actually known that Stein discrepancy can be blind or at least insensitive to regions of high probability which are spatially separated. And it's also not invariant to reparameterization, which I think is probably the case for most generalized Bayesian procedures. The question of calibration remains open for generalized posteriors in general, and we've used a heuristic due to Lidden, which worked reasonably well in our experiments, but there's not theoretical support for this approach, and I think it's also got some weaknesses which we can maybe talk about later. And of course, I've shown you experiments which are all for Euclidean data. The framework is actually general, so Stein discrepancies can be done for discrete data on manifolds, very general data, and we've not presented any experiments with those today. So there's lots to explore. Thank you very much for sort of putting up with the juggling of the slides and the presentation and everything. I hope it was okay. Here's the link to the preprint if anyone's interested to learn more. And just a quick announcement. This isn't announced yet, but it will be in the coming days. There's going to be a meeting at the RSS in London on Stein's method in computational statistics, and it'll be on the 8th of December. There'll be tutorials in the morning, research talks in the afternoon, and a poster session at lunchtime. And if you'd like to come along, just look out for the announcement on the RSS website in the coming days. If you'd like to present a poster, drop me an email, and we'd be very happy to host you. And thank you very much.
Yeah. Thanks, very nice. You don't have to repeat that. So there's two questions, right? One is dealing with the intractable likelihood, and then one is the idea that the model isn't necessarily the right model, you know, and you're dealing with both of them, right? But so if you're more in the scenario where you want to deal with the intractableness, actually, maybe either the model is right or it's not far from right. I mean, I thought I could see from some of the graphs that perhaps you would pay a bit of a price for doing this compared to normal phase, which I would expect. Is that right?
Yeah, so let me just repeat Sam's question for those on.
Actually, I'll just ask the second one, so you don't have to.
Oh, yeah.
I was just going to ask about whether you think you're choosing beta, you could choose beta in a better way, because I think that's about calibrating those two things.
Yeah, so thanks, Sam. So the question was, if we're not concerned with robustness, but we just want to benefit from the computational convenience of this, are we paying a price in terms of the efficiency of our estimation? And can anything be done about that, for example, by changing beta or finding a better way to select beta? It's a great question. I like this example because it suggests that there's not a huge difference in the efficiency of the procedure. But in general, I wouldn't really be able to give you a definitive result about our method not sacrificing efficiency. We've got 4 experiments, of which only 2 we can do Bayesian inference for. So I've only got 2 examples in which, so this one looks great. No loss of efficiency as far as I can tell. In fact, I think it might be a slightly overconfident. But, and the other experiment where I think so this is the well-specified regime, right? And our posterior is twice as big as this one. So there's a loss of efficiency there. Is this due to estimating beta or the choice of the discrepancy or both? That's unclear. I don't think you could. So efficiency is more than just selecting beta. It depends on the loss function as well. So although our approach to selecting beta has limitations, it's not clear that fixing this would resolve any loss of efficiency. It's a great question. This is all open questions essentially. One proposal for how to improve this could be to use a determinant instead of a trace, for example, because determinants quantify volumes of credible sets and things. And do you want to unmute and ask a question, please?
Yeah, I will put my face there as well. I don't know how I appear in the room. Perhaps a massive head or something like this. But in any way, so very interesting stuff. I have heard the talk by Jeremiah at Warwick last year, but I can see it involved. I have 2 questions actually. So the first one is that there's a requirement for differentiability of a quantity. Is this the normalized or the unnormalized density that you require differentiability of?
Oh, I'm sorry, Yannis, that was very quiet. I caught almost everything. So you're asking is something from the normalized or unnormalized density? Sorry,
sorry. I think there was at some point early in the slides a requirement about differentiability, but I didn't catch whether it was for the normalized or the unnormalized density.
So there was a comment about
differentiability.
Invertibility.
Differentiability.
Sorry, right. I'm with you now. Sorry. For some reason, the sound is almost inaudible. So what we require. You're saying in terms of implementing this procedure, or in terms of analyzing it theoretically?
Both, because I think differentiability of the unnormalized density is fine. It's an easy requirement, but if it's a differentiability of the normalized density, this can be a bit trickier for some models.
Right. Okay. Yep. That's a great question. So sorry for the communication. So the question is, what do we require in terms of differentiability, and is this limiting in some way? So what we require is the gradient of the log of the intractable likelihood.
Mm-hmm.
But let's remember what the intractable likelihood is. So it's this this quantity here.
Mhm.
So if I take the log of that, I've got the log of the numerator minus the log of the normalization constant. And when I differentiate, that log of the constant will vanish. So what I'm doing when I compute the gradient of the log intractable likelihood is I'm computing the gradient of the log of the numerator. So typically that is accessible. So if we think about something like an Ising model, that's actually specified, just using the numerator. So I require the derivative of the log of that, which is just the derivative of this thing here. So actually getting these derivatives is quite straightforward, because most of these intractable likelihood models of this kind of intractability that I've seen, they're all exponential family type models. So it's just looking at what's in the exponential family and differentiating it. So I think typically that's quite a weak requirement.
Right, so it's the, sorry, I thought it was the gradient with respect to the parameters. That's why I got confused. And the other question is what is really n? So this is one of my favorite questions in statistical modeling. So you need to have a precise value for n, right, for generalized Bayesian inference. But what happens, for example, the classical example is when you have, for example, n Bernoulli independent identical distribution, which, as far as likelihood difference is concerned, is the same as a single binomial. And also when you have like processes or data which can only be assumed realistically to be realizations of a single a multivariate process. So a single realization of a multivariate process. So what do you set n to be there?
Okay, so that's an interesting question. I've not given this much thought before. The question for those in the room is, what is n really here? So Jonas gave the example of having n Bernoulli random variables, and that being equivalent to having one binomial random variable. So I think we're talking about how we encode the data set. And this generalized Bayesian procedure would not be invariant to how you do that. So there's a choice to be made, so that's a great point. And whether it is advantageous or not to have larger n, so larger n would correspond to essentially smaller state spaces, which is typically a good thing to have, because it makes the analysis and the inference easier. It's a great question, Jonas. I don't know how to give you a useful answer. If we take an example, then n in this kind of POTS type model is one spatial image. So this is a spatial image where each pixel in the grid takes one of 4 different colors, and the colors represent something like the sea or the land or forest or buildings. And each image like this is one data point. So when you take a large collection of satellite images, you have n data points. That's the kind of setting we're thinking about. So does that help at all? I feel like I've not really said anything useful or surprising.
No, I mean, it makes sense, but in many times, for example, network applications, right, n is realistically 1, right, or even time series. If you have, unless you have like some short memory or stationarity conditions, n is still realistically 1, right? So would this somehow impact?
Oh, okay, yeah. So if I reinterpret the question as what kind of pathologies do we expect this inference procedure to show at small n? All sorts could go wrong. That's a bit unfair. But the sorts of things that are going to go wrong are estimating the information matrices that are involved in choosing beta. So these information matrices we use plug-in estimates that are valid asymptotically. So the first thing that's going to go wrong is these matrices will be estimated so badly that this beta will default to a value of 1, and that means that you may not have the efficiency of a Bayesian procedure, for example, because you're not lending enough strength to this this likelihood type term. So that's probably what's going to go wrong in small n. You will perhaps suffer efficiency losses. I think that's an effect we've inherited directly from the way of setting beta in Lidden. This is a general open problem that may be fixed in the future.
Yeah, so one way that, I mean, this is not a question that I haven't dealt with. I mean, I keep asking this question for myself for several projects I'm running. So one way to go around it is, instead of scaling with n, to scale with a variance-covariance matrix, which somehow takes the place of n. So for example, in classical asymptotics, you would use the Cholesky decomposition of the Fisher information, for example, or the square root of the Fisher information, right? So instead of having square root of n times beta hat minus beta, you have the square root of the Fisher information matrix per observation times beta hat minus beta. And this somehow would scale according to the likelihood instead of according to the dimension of the data representation in the computer memory, if that makes sense.
Okay. That sounds very interesting, but I need some thought to pass it properly. Can I drop you an email after the?
Yeah, of course. Yeah, of course. Yeah, thank you very much for a very interesting talk. I have to go. Cheers.
Sure. Thank you.
I have a quick question. I'll ask it really quickly. So if you're doing, I've used ABC a long time ago, but ultimately you need to make a choice to choose summary statistics, which and use distance. And obviously here you didn't do X is going to be Euclidean, but a lot of the time it isn't. So to what extent, I mean, if you do ABC, basically by not targeting the original posterior, you have a perturbed posterior through these summary statistics. To what extent is that choice, the effect of that choice of summary statistics, because we presumably do somewhere in the kernel here, how is the effect different here to what would have been with ABC?
Yeah, so Joanna's question is, does this procedure inherit the same sort of issues of ABC, in that ABC has a choice of summary statistics which strongly determines the properties of the posterior? I think you're right to draw that analogy with the kernel, because that's well, yeah, I mean, that's almost entirely determining your posterior as well. In ABC, we've got some approaches to selecting summary statistics. For example, the Fernhead and Prangle approach. And I guess our analog here is what we've got some theory which says, well, we need K to satisfy certain assumptions for consistency and asymptotic normality, and also certain assumptions for bias robustness. So that constrains our choice. But yeah, in general, it's true. We're perhaps in a slightly weaker position because we don't have an optimality criterion. In ABC, the Fernhead and Prangle approach is quite nice because it gives you an optimality criterion, but we don't have that here. So it's a completely valid point. I feel like maybe Jeremias or Takio or FX might want to.
So actually, you could show that ABC posteriors are special based on the generalized basis. Like a particular part of the short workshop paper, which is actually really straightforward. So in that sense, it's very related. But the choice of summary statistic doesn't, in my mind at least, have a direct correspondence.
Oh, okay. So Jeremias's view was the opposite of mine, just for those unseen. So
Boris also wanted to respond to Stein with the efficiency. There is a paper by Arnold Zellner from the late 80s in the American statistician called Basic Inference is Optimal Information Processing or something like this. And what it shows is that if you come from a standpoint of information theory, you can't compare it with the business theory. So it is the most efficient way of processing information under a correct model specification. So you definitely use efficiency if you update your release and your way.
Oh, no, that's a great point. Let me just say that to the microphone. So Jeremias points out that under correctly specified models, Zellner in the 80s showed that Bayes is optimal in the sense of efficiency. So therefore, what we're doing must be suboptimal in that setting, which is a great point. Okay, so was there one more question? So Alessia asks, in example 1, that was the normal location model, when talking about robustness, it seems that the procedure that we called robust is more robust to the position of the contaminator than the proportion of contamination. Is that implied by the type of robustness intrinsic in the model? That's a great question. So let's just have a look. So if you recall, the global bias robustness result talked about taking the location of the contamination and moving it far away. And it didn't say anything about what happens if you increase the amount of contamination, because we defined the posterior influence function as the derivative with respect to epsilon at 0. And what we see in this plot is that, well, when we try and move the contamination further and further away, the posterior doesn't change. So that's exactly what the theory said. But the theory didn't say anything about what's going on in the top row, which is what happens when we increase the proportion of contamination for fixed y. So that is absolutely valid, and we don't have any reason to expect that this would be robust to increasing the proportion of the data. But I'm not sure how you would formulate that theoretically, because obviously the most you can increase this to is 1, and it's sort of unclear if that's really contamination anymore. So you're absolutely right to point out that we've got theoretical guarantees for this, or something very close to this, because of course, you know, epsilon is still 0.1 and not 0. But we don't have any guarantees for this, and it may be the case that we can select the weighting matrix to deal with this kind of robustness, but we haven't attempted to do that. So yeah, thank you. That's a great question.